So what are organometallic compounds? Compounds containing a bond between carbon atom and metals are called organometallic compounds. So here are some examples. Organolithium compound in which carbon is bonded with lithium. Organomagnesium compound where carbon is bonded with magnesium, and organocopper compound, carbon bonded with copper. So in this example, you will see your carbon is containing electronegative charge and your metal is containing electropositive. This means the electron density on carbon is very high. Carbon is electron rich. So just we take one example like methyl chloride. We know chlorine is more electronegative than carbon. So it withdraw electron toward itself through inductive effect. So this is electrostatic potential map. It will tell you where the density of electron is high. So red portion tells you high density of electron which is toward chlorine, and blue tells you electron density is very less and it is in methyl. But when in case of organometallic compound like methyl lithium, you can see the electron density on carbon is very high compared to lithium. So what decide the magnitude of electronegative charge on carbon atom? So here we come the electronegativity. Lithium electronegativity is 1, carbon electronegativity is 2.5. 2.5 minus 1, you will get 1.5 difference. And if you do 2.5 minus 1.2 of magnesium, you will get 1.3. So this difference is large. This means carbon lithium, the magnitude of electronegativity charge on carbon is very high compared to carbon magnesium. Also you can compare other metal ion like carbon and zinc. So carbon is 2.5 and zinc is 1.6, you will get 0.9. So carbon bonded with zinc is less nucleophilic than carbon bonded with lithium. Carbon magnesium and carbon lithium compound reactivity is very high compared to carbon bonded with zinc or carbon bonded with copper. So let's take an example. When you treat acyl chloride with methyl magnesium bromide, this is called Grignard reagent. Okay, you will get tertiary alcohol. I will explain you later why you get tertiary alcohol and why you don't get this product. And when you treat acyl chloride with methyl copper lithium, you will get ketone. So this means in methyl copper lithium complex, only one methyl group is reacting on this compound, whereas in methyl magnesium bromide, which is highly reactive, first methyl group will react at this position, it will make ketone like this one, and then this ketone further react with one more methyl group of methyl magnesium bromide. This will give you tertiary alcohol. This means the reactivity of your Grignard reagent is much higher than this methyl copper lithium complex. Another example we can take, this is alpha beta unsaturated carbonyl compound. So if you react this alpha beta unsaturated carbonyl with methyl copper lithium, your methyl will react on beta carbon and you will get this product. This is called Michael reaction, Michael addition reaction. While this is not, this product will not form when you react it with organomagnesium reagent, because your organomagnesium reagent will react with this part. Okay, so what is Michael addition reaction? You need alpha beta unsaturated carbonyl compound in your Michael reaction. One is alpha beta unsaturated carbonyl compound, and in Michael reaction, Michael addition, there happen nucleophilic addition of carboanion. So you will create carboanion with this base. This base will abstract one hydrogen from here and it will generate carbanion, and this carbanion will react on this beta carbon of alpha beta unsaturated carbonyl compound. So here I have shown you the reaction mechanism. So your base is abstracting hydrogen, creating carbanion. This carbanion is stabilized by these two oxygen. By resonance, it makes resonance stabilization of this carbanion, and this carbanion further react with this beta carbon. So this carbanion, this methyl will react on this beta carbon, and you will get your product 4, and from product 4 oxygen will abstract so this carbon will abstract hydrogen and you get compound 5. So this is Michael addition reaction. Now we will talk about organolithium and organic magnesium compound. We will study these two organometallics together because their reactivity is very much similar. So this is organolithium compound and this is organomagnesium compound. It is well known by the name of Grignard reagent. So Victor Grignard received Nobel Prize in 1912 for this organomagnesium compound. So these both organometallics are highly reactive. And how you prepare this organolithium and organomagnesium compound? First you take organohalide. When you treat organohalide with the lithium, it will give you organolithium and lithium halogen compound. So in this case, your R can be alkyl chloride, aryl halide, or vinyl halide. Similarly, if you treat organohalide with magnesium in presence of diethyl ether, you will get your Grignard reagent. Okay, and this formation of organomagnesium or organolithium compound occur via radical intermediates. We will study this in future, how it will prepare. Now we come to reactivity of halide. So vinyl iodide, when react with magnesium in presence of diethyl ether as a solvent, it will give you Grignard reagent. The order of reactivity is iodine is much more reactive than bromine and bromine is much more reactive than chloride ion. So diethyl ether has its own role. And what is its role? So let's take example when R is alkyl or halogen is iodine. When you treat with magnesium, this reaction happens very fast. And what diethyl ether do? It stabilizes this Grignard reagent. So your diethyl ether function as a Lewis base and stabilize the Grignard reagent. But when your organohalide contains chlorine, you use THF as a solvent. The reason is chlorine reactivity is very less. When you treat this organochlorine compound with magnesium, you need to heat the reaction system. And this is the reason we use THF as a solvent because diethyl ether boiling point is very less. So you cannot use diethyl ether when the your starting material is organochloride. Now we will come to some reaction of organolithium and organomagnesium compound. So your Grignard reagent react very fast with water present and it will give you alkane. You can see the difference of pKa is very high. So this reaction is irreversible. This is the reason whenever you perform reaction with Grignard reagent, you generally use dry solvent like dry THF and dry diethyl ether. Even a trace amount of water react very fast. Next, if you want to deuterate your compound, in place of water you can use deuterated water. So you will get your deuterated product. So what is the problem with Grignard reagent? The first problem, I told you it react with water very fast. Even a trace amount of water react and it destroy your Grignard reagent. And second thing, whenever your starting material contain free hydroxyl group, free NH group, SH group and acid group, this Grignard reaction will not happen. Okay, so your Grignard reaction is not compatible with any of these chemical species. Some other reaction of Grignard reagent. So your ketone react with Grignard reagent will give you tertiary alcohol. So this is the mechanism. So this is your ketone. We know oxygen is little bit electronegative. It will create a carbocation here. And we know we can take methyl magnesium bromide. This methyl has negative charge, magnesium has positive charge. So your nucleophile will attack on this carbon cation. It will give you RCO negative MgBr and this R and methyl. So now this there will happen if you treat it with H3O plus. This oxygen will abstract one hydrogen and you will get your tertiary alcohol. Now reaction with epoxide. Your Grignard reagent react with epoxide will give you primary alcohol. So the mechanism is oxygen will withdraw electron, it will create carbocation here. So methyl magnesium bromide. Now you know what kind of reaction will happen here. This will react here and it will give you methyl and OMgBr. Next, with the hydronium, this will abstract one hydrogen. You will get your primary alcohol product. Reaction happened with carbon dioxide, you will get carboxylic product. So its mechanism is oxygen will withdraw electron, create partial positive charge here. So again this methyl will react here. It will give you CO negative MgBr, okay, and methyl here. And this will abstract hydrogen from hydronium ion and this will give you carboxylic acid. And similarly with ester you will get tertiary alcohol and its mechanism is this is your ester react with methyl magnesium bromide. This methyl act as a nucleophile, react on this carbocation, you will get oxygen negative methyl OMe. So this electron will return back and OMe is a leaving group, so you will get your ketone. And we know ketone when react with Grignard reagent gives you tertiary alcohol. And reaction with nitrile will give you ketone and the mechanism is I have shown you here. Nitrogen will withdraw electron, then this R2 will react here, will give you first your product and further protonation. First protonation happen, second protonation happen, and finally this process will continue and there is loss of ammonia gas and finally your ketone. So this is the mechanism of reaction of nitrile with your Grignard reagent and you will get ketone as a product. So now I have shown you the reactivity of Grignard reagent and various reaction, how you will get tertiary alcohol, primary alcohol, acid and ketone as a product. Now another organometallic compound is lithium dialkyl cuprate, which is also known as a Gilman reagent. When you treat organohalide compound with 2 equivalent of lithium, you will get an organolithium compound. When further you treat organolithium compound with 0.5 equivalent of copper halide or any copper salt, you will get your Gilman's reagent, which is lithium dialkyl cuprate. So this R group can be alkyl, aryl and vinyl. Gilman reagent are nucleophilic in nature. So what is the advantage of Gilman reagent over Grignard reagent? Or you can say the difference between reactivity of Gilman reagent and Grignard reagent. So your Gilman reagent, when it react with acyl chloride, it will give you ketone, right? And but when you treat with Grignard reagent, first it will make ketone and further one more Grignard reagent will react, will give you tertiary alcohol. And your Gilman reagent, when it react with alpha beta unsaturated carbonyl compound, your R group will attack on this beta carbon and you will get your this Michael addition product. But it is not possible with Grignard reagent. So some of the reaction of this organo copper lithium complex are Corey-Posner reaction, which is also known as White-Side-House reaction. So when you treat your organocopper compound with organohalide, you will get a coupling product and some byproduct. Order of reactivity of halides are same. Iodine is much more reactive compared to bromine and chlorine. Your R2 group can be methyl, primary, vinyl, or aryl. Okay. So in this reaction, your R2 or R prime, it is primary or secondary, but it cannot be tertiary, because in case of tertiary alkyl halide you will get elimination product. Also with secondary alkyl halide you will get elimination product, but here are some exception. When you treat organocopper lithium compound with cyclic iodide, you will get your product. Now we talk about stereochemistry. So stereochemistry will remain same for both reactant. Okay, so your E will react with Z, will give you E and Z. So your E part was with copper, so it is here, and G part was with organohalide, so it will remain as a Z. So there happens no inversion of configuration. Like if you treat this your Gilsman reagent with this iodine, the stereochemistry will remain same. No inversion of configuration. Another organometallic compound is based on zinc, and this is by the name of Simmon Smith reaction and carbenoids. So it is same reaction. If you treat your organohalide with zinc in presence of diethyl ether, you will get zinc complex. And carbon is electronactive than zinc. Okay, and ionic character is less. So we know the difference of electronactivity of CMG is high. So Grignard reagent have greater ionic character, but difference in electronactivity of carbon zinc is less. So organo zinc reagent is not ionic in nature. It is much more polar covalent rather than ionic. So how you prepare your Simmon Smith reagent? Okay, if you treat diiodomethane with zinc copper couple, you will get your iodomethyl zinc iodide, which is called Simmon Smith reagent. And where you get this zinc copper couple? When you treat zinc dust with copper chloride or copper sulfate, you will get zinc copper couple. Then you treat zinc copper couple with diiodomethane, you will get your Simmon Smith reagent. What is the application of Simmon Smith reagent? So Simmon Smith reagent is used for cyclopropanation. It will make a cyclic compound across this double bond. You will see a cyclopropane structure here. So wherever there is a double bond, this Simmon Smith reagent will create cyclopropyl group. And regarding stereochemistry will remain same. There will not be any inversion of configuration, but there will be retention of configuration. So in reactant there is trans, in product there will be trans. In reactant there is cis, in product there will be cis. So you see your Simmon Smith reagent function as a methylene donor. And when we talk about carbene can also prepare cyclopropyl structure. Okay, and if you see the structure of carbene, it reacts as a electrophile. Okay, because its octet is not complete. There is 2 to 4 to 6 electron. So its octet is not complete. If you see it other way around, it has 2 lone pair of electron. So it has nucleophilic in nature. So carbene work as electrophile as well as nucleophile. And how you prepare this carbene? When you react chloroform in presence of strong base, generally potassium tertiary oxide, it will abstract this hydrogen. And same time when hydrogen remove, chlorines come out. And this is also called alpha elimination, because both hydrogen and chlorine is coming out from same carbon. So this is called alpha elimination. And your product will be dichlorocarbene. So when your dichlorocarbene react with this double bond here, it will give you this cyclopropyl structure with dichloro group present on it. So this is the drawback of reaction with the dichlorocarbene, because you get cyclopropyl structure but it remains substituted, or they remain chlorine group in the system. But your Simmons Smith reagent, it will directly give you cyclopropyl. So this was the main advantage of Simmons Smith reagent compared to carbene. So stereochemistry in reaction of carbene is same. You started with trans, you end up with trans. You started with cis, you end up with cis. So there is a retention of configuration. Finally, the summary. We study about Grignard reagent, and I said in Grignard reagent there is magnesium. The metal is magnesium. Number 2 is Gilman reagent. Metal is copper. Number 3 is Simmon Smith reagent, and in this case your metal is zinc. Regarding stereochemistry, there remain retention of configuration. I have shown various reactions where you prepared like tertiary alcohol, ketone and ester product. Okay, so I have shown you the advantage of Gilman reagent over Grignard reagent in term of reactivity, where Gilman reagent, when it react with acyl chloride, it will give you ketone. But your Grignard reagent, when it react with acyl chloride, it will give you ketone first, then another Grignard reagent will react, will give you tertiary alcohol. And yes, Simmon Smith reagent, cyclopropane ring formation. So wherever it will see double bond, it will give you cyclopropyl product there.